Yeah, thank you very much. And yeah, thank you to the organizers for organizing this conference. It's a pleasure to be able to speak to everyone. Everyone's coming from all over the place. So I'm going to talk about some recent work that I've done with a couple of collaborators on stochastic and private non-convex outlier-robust PCA. And this is joint work with Chenyu Yu, who's now a graduate student at Princeton, and my former advisor at the University of Minnesota, Gilad Lehrman. The basic setup for the problem that we're studying, right, is that we want to find efficient methods for dimensionality reduction due to the fact that lots of the data we see these days are very high dimensional. And on the other hand, we want methods that are robust to outliers, right? So what if, say, an adversary comes along and corrupts a small percentage of your data set, right? You want your method to not be sensitive to those sorts of things. And what we've found through our examination of this topic, in particular by looking at this problem of outlier-robust PCA, that non-convex optimization methods can be both efficient and robust. And we'll see this sort of play out today within the context of this work. And just some more motivation in terms of applications. And this genes and geography example we'll sort of come back to at the end because it's sort of an important motivator for dimensionality reduction with privacy, which is one of the driving applications of this work. But we see low dimensional constraints arising in lots of different places, right? Things like images exhibit low dimensional structure, and this is the content of, further things like the manifold hypothesis. We see low dimensional constraints come up in places like 3D reconstruction and computer vision, as well as, the genetic makeup of people, right? We see patterns in terms of how people from similar locations in terms of their genetics tend to relate. And so the goals of this work were to first extend our past work into stochastic and mini batching variants to be able to work in settings where we don't want to do gradient descent on a full data set. And we also want to be able to incorporate noise into our methods so that we can make our data sets, make our methods differentially private. And within these settings, we don't want to lose our mathematical guarantees. And so these are sort of the main goals that we went into with this work is, can we extend this past work into this setting? And I'll go a little bit more in depth in a second into what these past results and methods were. So an outline of my talk today. I'll first give a background on this outlier-robust PCA, which we'll abbreviate as ORPCA. Sometimes is also called robust subspace recovery. I'll talk about what that is, as well as the method that we look into for solving it. I'll talk about how we extend this to stochastic optimization and what sorts of bounds we're able to prove in this setting. And then I'll give a specific application of these methods in differentially private outlier-robust PCA. So the main idea behind outlier-robust PCA is that when we think about subspace modeling and trying to reduce dimensionality of data, PCA and your typical subspace estimation methods just don't cut it. But if I have this data set on the left, where I have these x's are low dimensional, lying near some line, and the outliers are perhaps corrupted points that no longer lie near this line, and you compute PCA on this data set, you'll find something that deviates from this, obvious structure that you can see with your eyes from this data. Now, the outlier-robust PCA problem would say, within a data set where some points lie near a low-dimensional subspace and some points are corrupted away from that subspace, can I actually recover that subspace that's spanned by what are called the inliers? Okay, so we have a data set that's separated into two parts, inliers and outliers. And the goal is to return an L, a subspace, right? Here, the G stands for the Grassmannian of R-dimensional subspaces in R to the capital D, such that this subspace will approximately span the inliers. And so here we see that this subspace is this line. Now the solution sort of draws on classical ideas in robust statistics, and that's how do I take a method that is based on something like least squares and make it robust? And the sort of classical way of doing this is to go from a mean estimation problem to a median estimation problem, where instead of minimizing the sum of squared distances, I minimize the sum of unsquared distances. So we see at the bottom is the typical PCA problem as written as a least squares problem, where I'm optimizing over matrices with orthogonal columns, right? And so this term inside is the distance between the point xi and the span of w. And so if I'm minimizing the sum of distances squared, I find the PCA subspace. Now, if I remove the square, this would be an analog of a geometric median for finding subspaces. And this is the energy that we seek to minimize. Right? So minimize the sum of the unsquared distances between points in the span of W. And we examined this energy for a while, and it turns out that this energy is very well behaved. And this was sort of our main theorem in this area from our work in 2019 on what we call a well-tempered landscape. The essential idea is that if this data set that can be partitioned into inliers and outliers satisfies some generic stability condition that I'll go into in a second, then a geodesic gradient descent method with PCA initialization, as well as a specially chosen step size, will converge linearly to this underlying subspace, right? The subspace that's spanned by the inlier points. From now on, I'm going to assume that the inliers are noiseless. And so we see what this means in practice is that given a data set where I have inliers that lie near a low dimensional space and outliers that sort of permeate in the ambient space, my energy landscape is well behaved. And you end up seeing a large basin of attraction around a sharp minima that corresponds to the low dimensional subspace. Okay, and we see that in both of these examples. Here you see, for example, in this case of trying to find a one-dimensional subspace in R2, that when the angle is pi over 2, right, which is just the y-axis, I have this sharp minima here. Okay, so let's dive into a little bit more what these various things in this theorem mean. So the first thing is the stability condition, right? What is this condition that my data needs to satisfy? And essentially what it is a condition on how well the inliers fill out this under this low dimensional subspace. And here this little d should actually be a lowercase r. So this is a function of that is the rth eigenvalue of this sort of scaled sample covariance of the inliers. And on the other hand, we have this alignment term for outliers. And you can sort of think of this as being proportional to the square root of n times the top singular value of the outlier matrix. Suffice to say, though, that this inlier term measures how well the inliers are spread on the subspace, and the alignment term, as we call it, measures how aligned the outliers are in any given direction. And the stability condition is then that this linear combination of these two terms, right, the permeance minus the alignment, is greater than 0. And when this is the case, we end up getting this well-behaved neighborhood around an underlying subspace, right? So that corresponds to that sharp minima that you saw in the previous slide occurring within a ball of radius rho. Now that breaks down the stability condition. What about the method? The method used is geodesic gradient descent, where we're doing gradient descent on a manifold. And here the manifold is the Grassmannian of little r dimensional subspaces in RD. And essentially how Riemannian gradient descent methods work, or geodesic gradient descent methods work, is you determine a step direction v in the tangent space at your current subspace L, and you move along that v in the tangent space, and then use the exponential map to go back down to the manifold. Okay, so here we see that to update my current subspace, I take a step along the tangent space and I project back down to my manifold. Now, finally, there was this choice of step size that was this geometrically diminishing step size. Essentially, you can think of it as a piecewise constant step size where every little m iterations, I shrink my step size by a factor of 1/2. And so I have this sort of ladder of step sizes. Now, just to give you a little bit more details on this gradient descent method that we use, because it will come up again later on when we talk about the stochastic versions. When we think about Euclidean gradient descent, what you need to actually determine how to run the algorithm is a notion of gradient and a notion of gradient update, right? So in Euclidean space, right, to compute the gradient, that's just an element of the same space that you originally are sitting in. And the gradient update is just adding the gradient to your point. And you iterate to step along these gradient directions. Now, as I mentioned, the space of all directions for a manifold is the tangent space, and updates need to move along geodesics. So to do a gradient descent update for a method, what we need to do is we need to compute the Riemannian gradient. Okay, and the Riemannian gradient is an element of this tangent space. And here you can compute it as a sum over all of your data of this term, right? So this is really just me differentiating that cost function that I had written down earlier. There's an extra term here you may notice if you try to compute this yourself. That's the identity minus WW transpose. This corresponds to, after you compute the derivative, projecting it orthogonal to W itself, right? So I minus WW transpose projects orthogonal to W. Now, if you actually wanted to implement this method, right, how do you implement the exponential math? And if you want the explicit update, I've written it here for you, right? So what you can do is if I want to update to say that my new subspace is the exponential math applied to the minus scaled gradient, what I can do is I can take my minus gradient, which I wrote down here, and take the SVD of it. After taking the SVD of it, I have a closed form for how to write down what a Grassmannian geodesic is in this direction. And so you can use this, right? It's just a product of the matrices from the SVD with cosines and sines that will then give you your updated subspace. Right? And one of the things you notice is that this really is a bona fide update along the Grassmannian because this update ends up being invariant to the choice of basis that you chose for WT. Okay, so that was some sort of background on what we had shown before. So again, in simple words, we have a generic condition that ensures that an energy landscape is well behaved. This well-behaved energy landscape leads to fast convergence of a gradient descent method. What happens when we try to extend this to stochastic methods, right? Do stochastic methods still converge quickly? Right, and so the methods that we consider in this paper are three. Okay, so essentially you can think of them all as variants of more generally stochastic geodesic gradient descent. But essentially you can think about a noisy gradient descent method where at each iteration I add a noise matrix to my gradient. I could, instead of considering the full gradient, mini batch my gradient at each iteration and only consider a subset of the points, which is going to be x sub t, right? So this is just the mini batch at iteration t. Or I could consider noisy stochastic geodesic gradient descent, where I use both mini batching and noise. Okay, the noise may seem a little bit weird, right? Why do you want to add noise to your gradient method? But this has, a variety of places where it arises in the literature to do things like escape saddle points, as well as sampling algorithms like Langevin methods, as well as differentially private methods, as we'll see in a little bit. So the main theorem that we prove is about the convergence of stochastic methods for this outlier-robust PCA. Right, so we suppose that the dataset again satisfies the generic stability condition, which is the same as before in the case of noisy gradient descent, geodesic gradient descent. But for stochastic geodesic gradient descent, instead of a generic condition for the full data set, we now need an expected stability condition, where when we take the expectation over many batches, we need the stability term to be greater than 0. So we need on average that the inliers permeate more than the outliers when I sample my points. Okay, so with this condition, if I initialize with PCA, and I use, again, this small step size for a sufficiently small initial step, then I again get linear convergence to the underlying subspace L star with high probability. Right, so what this boils down to is if I shrink my my step size m times, right, so my total number of steps is mr, then the final error bound that I get on my output subspace is on the order of 1 over 2 to the r. Right, so this decreases linearly in the number of restarts, right, which is equal to t over m. So a few things to note about this. So one is that, right, this PCA initialization, why do we use this in both theorems? And again, it comes down to the fact that we have this local result, right? We get a local result because this is the local stability neighborhood. And we are able to guarantee that PCA can land you within the stable neighborhood so that the gradient descent methods can converge. Now, one of the interesting things is that, right, you may be familiar with, some results in stochastic optimization, and this doesn't look like a typical result for stochastic optimization. Normally, you expect stochastic methods to maybe converge on convex functions with rates that go like 1 over the number of steps or 1 over the square root of the number of steps. But here, right, you see a linear convergence of the stochastic method. And really the reason is that we have a sort of sharpness condition here, where we have a very sharp minima. And so if we use this specially chosen step size, you actually are able to get a linear convergence rather than these slower rates of convergence. Okay, so that's sort of the breakdown of the guarantee for these generic outlier-robust stochastic methods. Now, one of the real reasons we set about doing this work in the first place was to try to come up with private methods for outlier-robust PCA. Right, we have these sort of classic methods we've been studying for a while, as well as other methods you could think about making private. How does privacy actually fit in with this problem? And the type of privacy we consider is by now well known in the literature. So we consider epsilon delta differential privacy, where we say that a randomized algorithm is differentially private if for all output sets, right? So sets that fall in the range of your algorithm, and for all data sets X and Y that differ by at most 1 data point, we have this sort of bound on the probabilities of A of X and A of Y falling in this set S. So essentially what this is telling us, right, is that the epsilon and the delta are sort of your wiggle room in how close the outputs of the algorithm must be. And typically people achieve differential privacy by adding some mechanism to their algorithm, right? And the typical way of doing this is to do things like add noise to the algorithm, right? So randomize your algorithm by adding noise to the data set, add noise to gradients within it, or add noise somewhere to make it a randomized method. And the type of mechanism that we'll use is a Gaussian mechanism. Now, people have studied this Gaussian mechanism as it relates to optimization methods before. So in terms of differentially private optimization, people typically have studied this in the setting of empirical risk minimization, where the cost function can be written as a average of losses with respect to observations Zi. Okay, so if I do gradient descent on this objective, I would do the update x plus is equal to x minus the step size times the gradient. And to make it differentially private, I add noise to this gradient descent update. Now, what you can show is that if you run this noisy gradient descent method for t iterations, when the loss is L Lipschitz, and if you choose the noise on the gradient that you're adding to be on this order, right? So it scales with the number of steps, the Lipschitz constant squared, log 1 over delta, and it also is divided by n squared epsilon squared, then your method is guaranteed to be differentially private. Okay, and so this is sort of one of your classical results that applies the known differential privacy of this Gaussian mechanism along with a composition theorem to guarantee privacy throughout t iterations of gradient descent. Now, one of the things you can do is once you have a differentially private guarantee for, say, an empirical risk minimization method is to extend it to the case of mini batching. So mini batching here would correspond to taking subsets of size capital B of these observations Z1 to Zn. And so at each iteration, then I would take my mini batch here with indices I1 to IB, compute the gradient with respect to those only, and do my gradient descent update. Now, when you add this extra stochasticity from uniformly sampling the points ZI1 to ZIB, you end up gaining privacy. And because of this, you don't need to take sigma to be as large. Okay, so to have the same epsilon delta privacy, I can shrink my sigma squared by essentially a factor of b over n squared, right? So if the mini batch is much smaller than n, the noise I need to take is much smaller than n because the variance of these gradients will be very large, right? And so then the one observation, say, won't affect the outcome too much. Okay, so going back now, I have my results for geodesic gradient descent and its stochastic versions. And I can take these differentially private results for both full batch noise as well as mini batch noise and apply them to geodesic gradient descent or stochastic geodesic gradient descent. And when I do that, I get automatically a differentially private method, right? So if I run the method with these chosen noises, either in the case of full batch, I get the dp-GDD method. In the case of the mini batch, I get the dp-SGGD method. And I run for t equals t on the order, of n squared epsilon squared iterations for a certain number of restarts. Right here, again, you're constrained with the number of restarts by the number of total steps that you can take. And the chosen noise that you see above, then the final iterate will have a distance from the true subspace that's in the order of 1 over 2, 2. Again, you see this R factor appearing up here. So you get a linear convergence of this differentially private method based on how many steps that you can actually end up taking. Now, this is a with high probability result for a sufficiently large n, right? And essentially, n needs to be large enough so that the sort of step sizes work out. But in any case, one other thing you may notice here is that this total number of iterations t needs to be on this order, and this is so that that the noise is bounded, right? If the t is bigger than this, right? If you let t go off to infinity, then this noise actually blows up, and I need the noise to be constant. Now, to compare this with what you get if you try to do something convex, right? One thing you could do is just take out of the box differentially private optimization techniques and apply their convex results to a convex outlier-robust PCA algorithm. And so we choose to do this on the Reaper method. And the Reaper method essentially is a convex relaxation of this least absolute deviations or geometric median energy that you saw earlier, right? So here, instead of having the WW transpose, I relax that non-convexity to the set of matrices that are capital D by capital D that have eigenvalues between 0 and 1, and whose traces, this should be a little r, whose trace is little r, right? So the orthoprojectors onto rank R matrices have trace R. So you can consider noisy subgradient descent and noisy mirror descent on this, and you end up getting, after the same number of iterations that we just showed for GGD, expected error bounds that are on the order of 1 over epsilon n, right? So 1 over the number of iterations, 1 over the square root of the number of iterations. And this is more typical of what you see from for results for stochastic convex optimization. And so we really, end up seeing a large gain for a non-convex versus convex differentially private Outlier-Robust PCA. In both cases, I'm taking the same number of steps because I'm constrained by, again, not letting the noise grow to infinity, right? So t needs to be less than n squared epsilon squared. But in those steps, I get a much more effective error guarantee for the non-convex method when compared to a convex method. And again, it's due to this sharpness that you saw earlier that allows fast convergence of stochastic methods. Right? So rather than 1 over the number of steps, I get 1 over 2 to the number of restarts. The other thing I gain from this, right, and this goes back to one of the things I highlighted at the beginning of the talk, and that's I also want efficient methods. And in terms of the convex method versus the non-convex method, you really save in per iteration complexity as well. Whereas the, say, full batch convex method needs to store a capital D by capital D matrix at every iteration and compute the gradient, which takes on the order of n capital D squared operations. The full batch for geodesic gradient descent only takes NDR, right? So we're considering cases where the rank is much less than the dimension of your data. And furthermore, if you mini batch, right, so you don't actually compute the gradient on the full data set, you can reduce this even more, right? So we can get an exponential decrease in our distance between our estimated subspace and the true underlying subspace, with a very low per iteration complexity of the mini batch size times D times R, right? And the dependence on all of these constants can be seen in the paper. Okay, so I want to finish by looking at a couple of experiments just to demonstrate how this performs on some data. And what we proved really bears out in experiments. Okay, so here I'm showing some plots of the convergence with respect to both iteration and time for the different methods. On the top row, I have the non-mini batch versions, and on the bottom, I have the mini batch versions. And what you see, say across the top row, is that the non-convex method converges linearly as expected, and the convex methods converge with that rate that's 1 over, say, the square root of the iterations. And I don't know if the recording needs to start again. Should I continue or should I pause for a second?
I think you can continue.
Okay. So we see the fast convergence of the non-convex method versus the slow convergence of the convex method. Now, in the bottom row, what we see is, again, the same thing borne out, but for the stochastic mini batch versions, right? So again, mini batching allows you to make your method faster, as you see in the decreased running time when compared with the above, but you still get the same linear convergence, right? So everything here is a stochastic gradient descent method, and adding this extra stochasticity doesn't make you, say, lose in accuracy, and actually makes you much, much faster. Now, one of the things that I had shown at the beginning of the talk was this example of genes and geography, and this is one of our, say, motivating examples is, privacy is really important, especially for protected information. And this was an example of data where you can, project the genetic information of 1,300 individuals down to the top 2 principal components, and you end up seeing a picture of Europe emerge due to their genetic variation. Now, we don't have access to the full data set, so we generate our own stylized data set based on this, where we took the data of the top 20 principal components of the 1,300 individuals who made up this plot. And we multiplied them by a random matrix to project them back up into dimension 10,000, right? So we're trying to simulate our own genetic data. I also generate 1,000 outliers in the same dimension whose underlying dimension is 30. Right? So in this case, I'm trying to generate maybe some corrupted data whose points lie on a different low dimensional subspace. And I threshold all of them to obtain values -1, 0, and 1 to correspond to, say, discrete genetic data, right? Where they could correspond to different allele types. And what we see is when we run our methods on this very high dimensional data, PCA, of course, is not robust to the corrupted data, and so it doesn't output anything nice. But if we look at the other three methods, which are three robust methods, the geodesic gradient descent full batch method doesn't actually output anything useful. Whereas the differentially private stochastic geodesic gradient descent, the one with mini batching, does actually output a picture that's starting to look like this Europe picture again. Slight variations may be due to things like thresholding as well as noise. The SGD Reaper is maybe a little bit more useful than the geodesic gradient descent, but still not quite where this is at. So the real question here is, why is this outputting something nice? Well, this is not outputting something nice. And the key point is that the stochastic geodesic gradient descent method is allowed to use much smaller noise than the geodesic gradient descent method due to that mini batching. So we see that in practice due to the fact that the mini batching reduces the amount of noise you need to add to make a method differentially private. I can add a smaller noise variance here and still recover a good estimate of this subspace when, say, another method would not. Right? And really, this is due to the fact that these things are living in very high dimensions. So the noise ends up scaling very fast. Okay, so before I finish and conclude, I just want to mention one final thought related to this, and that's we set out to make our robust methods differentially private, and we did this by adding noise to gradients. But if you think about it, there is already an interaction between robustness and privacy, right? And this has been noticed by people in the past. And I just want to illustrate it in our specific case because it really points to the fact that, there's further room to actually explore the theoretical results here, right? So if we go back to the idea of stability that I had before, stability implies a well-tempered landscape, as we call it, which ensures local convergence of a geodesic gradient descent method. Now, if I assume a condition like the following, where I have my data set X, and I assume a stability condition on all subsets of my data where I remove exactly 1 point, right? So if the stability holds after removing 1 point for each possible point that I could remove for I equals 1 to n, then in this case, what this means is that the underlying subspace is output for both the full data set as well as the data set if I remove any single point from the data set. What this means is that my method is actually perfectly private because no single point actually influences the output of the algorithm. The algorithm will always output for these adjacent data sets this underlying subspace. All right, this algorithm is really deterministic in this case. So the question is, how does this robustness and how do these stability conditions actually interact with privacy, and how can you maybe use them to, say, decrease the amount of noise you need to add in an algorithm, right? Because this is private maybe without adding noise. But to conclude, what we've given it are proofs of convergence for these non-convex stochastic outlier-robust PCA algorithms. In differentially private noise setting, right, the non-convex methods converge much faster than the convex methods under this assumption of stability. And so our open questions, that we're really interested in pursuing more are things like, again, how do we think about the interaction of robustness of the energy with the differentially private optimization algorithms? And going back to something I mentioned briefly earlier, we talked about noisy gradient descent. One other potential application of this is to think about sampling algorithms, right? So this is a natural next step is these algorithms can be thought of as a Langevin algorithm on the Grassmannian manifold. And what sorts of mixing results can you prove for these sorts of energies? Okay, so I'll stop there and open it up to any questions.